Today's lesson is on the exponential function and exponential equations. So first I have written down the general form of an exponential equation, y equals a times b to the power of x. So some information about each of those letters. A cannot be 0. B has to be greater than 0, so b cannot be a negative number. And also, b cannot equal the number 1. So any number between 0 and 1, and any number greater than 1. And then the variable x is just your variable. So you're always plugging in numbers for a and for b as part of your equation, and then x is your variable. And then a couple other bits of information about a and b that will help you with story problems and with graphing. Whatever a is your y-intercept. And then b will always represent your rate of exponential growth or your rate of exponential decay. So in the next two examples, we're just going to practice filling out a function table that uses an exponential function. So for this function, f of x equals, we're going to do 1.8 times 2 to the power of x. And then to make a function table, we're going to pick values of x, plug them in, and then solve. So for x, -1, 0, 1, and 2. So if we plug all of those numbers into our function, we'll have 1.8 times 2 to the power of -1, 1.8 times 2 to the power of 0, 1.8 times 2 to the power of 1, and then 1.8 times 2 squared. So the reason we're doing this is a quick review on order of operations when you have an exponential function, and then we're going to kind of analyze what happens with our results. So 1.8 times 2 to the power of -1, you should get 0.9. And then 1.8 times 2 to the power of 0, 2 to the power of 0 is 1, and then 1 times 1.8 is 1.8. So just the order of operations that you need to remember, you're always evaluating the power first, because you do exponents first, and then you multiply by the coefficient. So the next one, 2 to the first power is 2, times 1.8 is 3.6. And then the last one, you should get 7.2. So now, after looking at this function table, I want you to notice how do these values increase? If you look, they are being multiplied by 2 each time. They're doubling. And now go back to your equation. Do you see the number 2 anywhere? Right there. And now, if you look here, we have 1.8 in our equation, and 1.8 showed up in our function table, and it's when it was matched up with 0. So, just like we talked about, the leading coefficient a is the y-intercept, which is the number that matches up with 0, and that b is the rate at which the exponential function increases or decreases, and in this case, it's doubling. So here's another exponential function, 100 times 1/2 to the power of x. We're going to plug in 0, 1, 2, and 3 into our function table. So I want you to pause the video and evaluate those 4 numbers first, and then I'll come back and we'll analyze our results. You should have gotten 100, 50, 25, and 12.5. So how did these numbers decrease? What are you multiplying each of these by to get the next number? And you're multiplying by 1/2. which if you look back in the equation, that was the rate, the exponential rate of. This time it's decreasing because you're multiplying by a number less than 1. And then if you notice, 100 is the number that matches up with 0 and is the leading coefficient of our equation. Now we have a story problem involving exponential growth. It says, suppose 20 rabbits are taken to an island. The rabbit population then triples every half year. And then how many rabbits would there be after 2 years? So I think this is a scenario that you could easily figure out, but the key is, can you write an exponential equation to represent the situation and then use the equation? So remember, the general form of an exponential equation, y equals a times b to the power of x. So now we just have to figure out what numbers in our story problem correlate to a, b, and x. Alright, so 3 things that will help us that you might want to write down is that a, because that's our y-intercept, it's also our starting amount. So how many rabbits do we start with? We start with 20 rabbits on the island. B is always your rate, and the rate, it says it triples. So we want to think that word, if it triples, then that means our b value is 3. If it was doubling, it would be 2, but in this case it triples. And then x, the number that you will plug in for your variable, is how many times does it triple? How many times does it triple? If it triples every half year, and they are there for 2 years. So let's first write the equation y equals 20 times 3 to the power of x, and now we have to figure out what number to plug in for x. So we want to think, let's see, it triples every half year, and they're there for 2 years. How many times does it triple? It will triple 4 times, because in 2 years there are 4 halves. So y equals 20 times 3 to the power of 4. Y equals 1,620. So 20 rabbits, if they triple every half year, in 2 years there'll be 1,620 rabbits. Alright, so now moving on to graphing exponential functions. I'm going to talk quickly about just kind of the general form of an exponential graph, and then we will actually graph 2 specific equations. So I'm going to do one example. Let's see, on the left we'll do an example of exponential growth, and on the right an example of exponential decay. So if something is going to grow exponentially, that means its rate, or the value of b, has to be greater than 1. And then just remember, we're talking about the general form of an exponential equation, a times b to the power of x. And we're referring to b. b has to be greater than 1 for it to be growth. But for it to be decay, it's not going to be negative, because b cannot be negative, but it's going to be between 0 and 1. So a decimal or a fraction in between 0 and 1. And what the graph looks like on exponential growth, it is going to be very, very close to the x-axis, but it will never touch it and it will never cross, and then it increases quickly on a curve. And then exponential decay, it's decreasing, so it's starting out and then it's decreasing on the curve, and it will get very, very close to the x-axis, but it will never cross it, touch or cross it. And that brings me to the word asymptote. Asymptote is, the definition is when a line on a graph gets really, really close, but to another line, in this case the x-axis, but never crosses it. So in this case, it's the x-axis, but an asymptote can have many other lines that it will get close to but never cross it, but for today's lesson, the asymptote is the x-axis. So for each of these, I'm just going to write just a general equation that would represent exponential growth. Y equals 2 to the power of x, because the base is greater than 1. Where this could be y equals 1/2 to the power of x, because the base is between 0 and 1. Alright, so now let's actually practice graphing an exponential equation. Y equals 3 times 2 to the power of x. So before we start, I just want you to think to yourself, will this be exponential growth or decay? And if you look at the base of your power, that's going to represent growth. Now I'm going to quickly just sketch on my graph, but I'm going to erase it, so I don't want you to graph this. If it's growth, that means you're going to have really, really small numbers, and then it's going to increase quickly. So the key to making a good XY table, you need both negative and positive numbers, and you never want numbers too large because they generally will go off your graph. And then you want just a couple negative numbers, but you don't want too many of them because you'll get really tiny decimals that will be difficult to graph. But let's make an XY table and actually graph this function. Let's pick -2 and -1, so a couple negative numbers, 0 and then 1 and 2, and see where that gets us. So if we plug in -2, 3 times 2 to the power of -2, remember, order of operations, 2 to the power of -2 is 1/4 times 3 is 0.75. And then if you plug in -1, you should get 1.5. When you plug in 0, you should get 3. When you plug in 1, you should get 6, and 2, you should get 12. So let's plot all of these points. -2, 0.75, -1, 1.5, 0 is 3. Hey, and that's the y-intercept, and if you notice here, that's the value of a. 1, 6, and then 2 already is off of our graph, up at 12. So I'm going to connect these to make my curve, but now I want you to be careful when you make the other part of your graph, because you're going to curve it and you're going to follow the x-axis, but you are never actually going to cross it. If your line crosses the x-axis, you'll lose some points because you have to follow the rules of the asymptote. Alright, last example. Let's graph this equation. Y equals 2/3 to the power of x. What is missing from this equation? It has the value of b, which is the base of your power, but there's no a. And in that case, what it really means is 1 times 2/3 to the power of x. And because b is between 0 and 1, this is going to be exponential decay. So we're going to make an XY table, but before we make the XY table, I want you to think about what will this graph look like. So I'm going to do a quick sketch that I don't want you to graph. Exponential decay is going to look like this. So when you are picking values for your XY table, you're going to want maybe a couple more negative numbers, because that's where you actually get easier numbers to graph, and then maybe only a couple positive ones, because now you're going to get numbers really, really close to 0, very small decimals. Alright, so XY table, let's pick, I'm going to choose -3, -2, -1, and then let's get just 0 and then 1 and see where that gets us. So if you plug in -3, 2/3 to the power of -3, you should get about 3.4. When you plug in -2, 2.25, When you plug in -1, you should get positive 1.5. And then when you plug in 0, you should get 1. And you plug in 1, you should get 2/3. Or 0.6 repeating. So now we have to graph these points. So -3 up 3.4, -2 up 2.25, -1 up 1.5, 0, 1, and then 1, 2/3. So if we connect these and extend the line, and then we can extend the other way with an exponential decrease from left to right. So there's your full lesson on an introduction to the exponential function. Good luck!